Section 5.4 is called conditional probability in the general multiplication rule. It's basically what we just did, except for things are not independent, so probabilities are going to start changing, but we know how to do that. Think about that card selection. If we've got to pick a king, it's a 4 out of 52 chance, but if we hold on to him, what's the probability that you get a queen? 4 out of 51. And at that point, guys, it's just going to multiply. It's all the only difference that's going to be happening, okay? So it says for OR probabilities, we're going to use the general addition rule. For and, this, and then that, we're going to use the multiplication rule. So before we get to the multiplication rule, we need to talk about conditional probability. It's a weird notation, but in quotes is written as it should be read. It's the notation of the probability of F given event E, meaning what is now F's probability knowing E has already occurred. Okay? So what's the probability of queen after you've pulled out a king and didn't replace them? That's what it's saying, okay? So let's make sure we can make it. This is, every year I mean to like edit these and I always forget to. It's that same exact chart that we dealt with on Monday, where there's 100 people total, 50 are males, 50 are females, 80 are right-handed, 20 are left-handed. But then I try to match the book with E's and F's and it gets a little complicated. I'd rather just use M and LH for left-handed, but okay? So our event E, this is the first thing that's happened. We know we've chosen a male, okay? Our event F is going to be the second thing, that's the left-handed. So they want us to compute the probability of F. So just what's the odds of picking a left-handed person? But then they also want us to compute the probability of F given we know we've picked a male to compare what that means, all right? So let's just focus on the probability of event F, picking a left-handed person. Well, how many total people are there to choose from? 100, and how many of them are left-handed? 20. Is everyone okay with that? No, like, tricky things there. So let's write that as 0.20. So basically, from the get-go, if I'm just randomly drawing a name from a hat, I have a 20% chance of picking someone that's left-handed. Now, what if I said, oh, I drew a name, but I can tell you it's a male. What are the odds of that happening? How have I narrowed it down? So instead of just probability of getting a left-hander, what's the probability of getting a left-hander knowing we picked a male? So now what is our denominator? 50. Why is it 50? Because we know we picked a male. And what's our numerator now? I heard it. I thought I heard it. 12. Because not only do we know we picked a male, we're just going to look at this column, and of those males, how many are left-handed? 12. So that as a decimal, I think, is at 0.24, guys? Yeah. So look how that has changed. So the first one was, what's just the probability of getting a left-hander? The second question is, what's the probability of getting a left-hander knowing you picked a male? And it's narrowed it down a little bit. We have a little bit more chance of it happening. So this is just a good example of showing you the difference between just flat out, we're picking from everyone, so everyone has a chance of being pulled, versus we know we picked a male first. So it narrows it down to not only how many total people we're looking at, but how many left-handers we're looking at. Okay? Why do we need to know this? Flip it over to the top of page 9. Because this little guy is like a short way of doing it. So that chart, guys, is what we just did right here. The probability of event F, given that E has occurred, is always just how many ways can E happen, and then how many ways do both of them happen. So this is the event that's already happened. Already happened. And then this is the probability that both happen. What do I mean by that? You guys keep your page to this formula, okay? Keep your page to this formula. The total number of how E has happened is on the bottom, and then the probability that they both happen is on top. You keep your page there, okay? I'm going to flip it over back to that chart and show you we just did this formula without knowing the formula. All right, what's the bottom? The probability of E, the only thing that already happened. Who do we know we already chose? A male. So how many males were there? 50. That's why it's our denominator. What's the numerator for your guys? The probability of being male and left-handed. Well, how many of them are male and left-handed? 12. and that's why it's the numerator. So we did it without even realizing we were using that formula. We said, okay, well, we've narrowed down the playing field. We know E already happened. There were 50 people, 50 guys to choose from, okay? So let's look at this problem. It says, the probability of a plane arriving on time is 87%. The probability of a plane arriving and departing on time is 83%. What's the probability that your plane departs on time given that it arrived on time? There's a lot of words there, but what we know, I'm going to write this. Given that is your conditional probability. The probability that we depart on time, given that it arrived on time. The probability that it departs on time, given that it arrives on time. So the second you see given that, do that vertical bar, that conditional probability, all right? When you do the conditional probability, the second thing is always what's already happened. We want to know the probability of departing on time, knowing it arrived on time. So you're sitting at your gate, you're like, I wonder if I'm going to get off this plane on time. So what happens, we're going to do our denominator here. What already happened? Our plane already arrived on time. Notice it matches this. What already happened? So what was the probability that our plane arrived on time? We're going to write plane arrived down here. And then following this formula, what goes up on top? The probability that it arrived and departed on time. So I'm just using words instead of E's and F's, okay? So I'm using this, oops, I'm pointing to it and you don't even see all of it. So what's the probability F happens given that E happens? Well, E already happened, so that's the bottom. And then this is what they share. And just go back to your two numbers, what you have, okay? Let's see what we can fill in. I always do the bottom first. What was the probability that when you're sitting at your gate that the plane just lands right there and arrives on time? Say it louder, you're right. 0.87, it was just told to us right there. Now that that plane is there, what's the probability that it's going to arrive and depart on time? 0.83. It's just the other number they gave us. Do you guys see that? The singular goes on the bottom, arriving on time. What they share, arriving and departing, goes on top. What do you guys get when you round to like 2 or 3 decimals? 9.5, is that about right? And that should make sense. Knowing that your plane arrived on time should bump the odds of you taking off on time, right? If it's late, that's hurting you. Worst case scenario, guys, if you don't know which one goes on top, which one goes on bottom, if you accidentally flipped these, you'd get a number greater than 1, and can probability be greater than 1? No. So that's your sign like, crap, I got to make the small number on top, okay? I wouldn't worry too much about this. We have 2 on our worksheet and maybe 1 or 2 on our homework, but really the reason why we want to know this is so we can get to this, okay? Of this whole formula, what do we care about? We care about the probability of E, and then you don't need to circle it, but we care about the probability of E and then F happening. So just think of math. If you wanted to get this isolated, what do you need to get rid of? The probability of E. If it's in the denominator, how do you get rid of it? You multiply both sides by it. And look at what that formula is. That's exactly what they did. The general multiplication rule just says the probability of E and then F happening is the first one happens no matter what. It's not changed. It's not affected. It happens. Times the probability of the second. But we have that conditional probability because the probability of second may or may not change, right? We might only have 51 cards to draw from now. This is how I kind of approach every single problem, just like with the addition rule. I always remember that minus part. I always remember when I go to my second one, has my probability changed at all? So let's look at this first one. Compute the probability of selecting a king and then selecting a queen without replacement. So the probability of a king and then a queen, keyword, without replacement, okay? So according to this, we're going to do the probability of getting a king first. His probability is not really changed or affected at all. But now we have to consider what's the probability of getting a queen knowing that we pulled a king. Okay? And I'm just mimicking the formula for now. I do not expect for you guys to write this generic formula out like this. I'll show you. I honestly would just go straight to the second row, and I'll show you what I'm talking about, okay? So I would expect for you to write the probability of a king and then a queen. But then what we do is we just go one at a time. The king's the first thing you're drawing. How many total cards are there? 52. Of those 52 cards, how many of them are kings? 4. All right. You pulled that king. You did not replace them. So how many total cards are there to pull now? 51. How many queens remain?
4.
All 4 of them, right? So I didn't pull a king, so all 4 queens are there, but I did pull a card. So that reduced my number down to 51. That's all that's saying, okay? The probability of getting the queen's a little bit different now. Multiply straight across the top, straight across the bottom. To like 3 decimals, what do you guys get?
4 over 6.
Oh, so you get, okay, we'll do that. We'll reduce. I think it's like 0.006 or something like that. Basically, in a nutshell, it's not very likely to get a king and then a queen, right? So this is what I'm talking about. When I go to do this and then that, so whether it's the green worksheet or the pink worksheet we're going to get, just think of what's the probability of the first thing happening. All right, you go to the second. What's the probability of the second happening? It doesn't change? Okay. It does change? Okay. You're just going to multiply them no matter what. Any golfers? Does anybody golf? We talked about this already. So my husband golfs, and he has like the longest drive ever, but he's not consistent. So that, like, he's always chasing his golf balls off into the woods or whatever. So he never buys golf balls. He just finds them when he's looking for his, and he'll just put them in his golf bag. So say this is my husband's golf bag. He has 20 Titleists, 8 Max Flies, and 7 Top Flights in his golf bag. I was told when you go golfing that you need to always have 2 balls when you go to drive, because if you shank one, you're right there ready to hit the second one, okay? So say we're going to get up and we're going to go drive our golf ball. What's the probability when I reach into the golf bag that when I randomly select 2 golf balls that they're both Titleists, all right? So the probability that they're both Titleists. It's a weird word to spell. Both Titleists. Well, when I go to pick that first ball, how many total balls are there to choose from?
35.
Where'd you get that?
I added all.
Right? So we know all of these are in the golf bag. So there's 35 total golf balls. So when we go to grab that first golf ball, how many golf balls do we have to choose from? 35. But of those 35, what type do I care about choosing? Titleist. How many of those are Titleist? 20. Okay. So I get that. I put that in my pocket. That's my backup ball. And then I go to grab a second one because I want to make sure I have one to actually drive with. How many total golf balls are there? 34 now because I kept that and put it in my pocket, right? How many total Titleists are left? 19, right? Does everybody see what happened there? So no matter what, when you're doing these back-to-back choosings and you're not replacing, your denominator always goes down, right? It went from 35 to 34. Your numerator may or may not go down based on whether you're worried about choosing the same thing back-to-back or not. So the card question right above, I didn't want to get a king again and a king. So all 4 queens were there. But in this one, I wanted a Titleist and then another Titleist. So when I picked this first golf ball, got a Titleist, and put it in my pocket, I have 1 less Titleist to choose from. Okay? So what do you guys get like to 3 decimal places?
3, 1.
Perfect. Thank you. So what gets confusing is that you want to put like a 2 there because you're picking 2 golf balls. You never put the number of things you're choosing. That's how many probabilities you're multiplying by, right? So since I'm choosing 2 golf balls, I have 2 probabilities. If I was choosing 3 golf balls, I'd have a 3rd probability multiplied right behind it, okay? Let's look at this next one. What's the probability that 1 golf ball is a Titleist and 1 is a Max Fly? I want to make a note here. Order is not implied. And what do I mean by that? In every other scenario, they told you what they want you to choose first and then what you want to choose second. But in this scenario, they just said, what's the probability that one's a Titleist and one's a Max Fly? Do they tell me in what order I got it? No. So what we have to be careful of is I could get a Titleist first and then a Max Fly, and make this happen, or I could get a MaxFly first and then a Titleist and make that happen. So we have to think about both scenarios, okay? So the probability of a Titleist and a MaxFly, a T and an N. Let's think of the first one. Let's say we pick a Titleist first. Well, how many total balls are there to choose from? 35. And how many of those balls are Titleist? 20. Is everyone okay with that? I put it in my pocket and I go to grab my second golf ball. How many total golf balls are there to choose from? 34. How many are MaxFlies though? 8. Is everyone okay with that? So this is just one scenario. This is the probability that I get a Titleist and then a MaxFly. And I'm going to put a big plus here because plus means or, right? This or this could happen. Ignore this scenario. Let's think about the other scenario. I want a MaxFly first. How many total golf balls are there to choose from initially? 35. And how many of them are MaxFlies? 8. Now that I've chosen a MaxFly, how many total golf balls are there to choose from? 34. And how many of them are Titleist? 20. Do you guys notice that it really doesn't matter in each scenario? The denominators are the same and the numerators are the same. They're just flip-flop. So really all you have to do is think of one scenario and say, okay, that could happen, but this could happen. So you could just double it. You can just times it by 2. All right? But if order is not implied, you have to think of the multiple ways it can happen. So when this is all said and done, guys, what do you get to 3 decimal places when you do all of that together? I think I heard it. 269. I know sometimes we're scared to shout out those answers. Is that 5.4?